Welcome back to the active suspension system. In an earlier video, we modeled the system from physics. We chose the input as voltage U, the output as displacement x, and the disturbance as the road bumpiness h. We derived a block diagram with two integrators. Today, we will replace those integrators with their transfer functions, then simplify the block diagram into the standard form. U goes through G1, then a summing junction where H enters, then G2, and out comes X. Our goal? Find G1 of S and G2 of S. The starting block diagram has these blocks. K converts voltage U to pressure difference. A converts pressure to the cylinder force. The cylinder force adds to the spring force, which depends on H minus X with constant C. The total force is divided by mass m and integrated twice to get position x. Finally, x feeds back into the spring force calculation. Before we start, let us recall the 4 block diagram tools we will use. Rule 1. Series connection. 2 blocks in a row multiply. Rule 2. Feedback. Forward G with feedback H gives G over 1 plus GH. Rule 3. Called Summation Move Type 2. When we move a summing junction past a block, we must compensate by adding the inverse of that block on the moved branch. Rule 4. Summation Move Type 3. 2 summing junctions can be merged or reordered without changing the result. 4 tools, 4 steps. Let us start. Step 1. Series combinations. First, K and A are in series, both constant gains. Combine them into one block, K times A. Second, the two integrators after the mass division are in series. The first is 1 over ms, the second is 1 over s. Combined, they give 1 over ms squared. Now our forward path is much shorter. U through Ka, then a summing junction where the spring force enters, then 1 over ms squared, and out comes x. The spring force still depends on C times the quantity h minus x. Step 2. Split the spring force junction. The spring force is C times the quantity h minus x. This means h and minus x enter through the same gain C. We can split this. C times h enters as one branch, minus C times x enters as another branch. Now we apply the Summation Move Type 2. We move the CH branch backward, past the KA block. To compensate, the CH branch must be divided by KA. But we want a cleaner form, so instead we move the input summing junction forward, past the gain C. The disturbance H is then multiplied by 1 over C. This rearrangement isolates the unity gain on H. Step 3. Close the inner feedback loop. The minus C times X feedback creates a loop. Forward path is 1 over ms squared. Feedback path is C. Apply the feedback rule. The closed loop transfer function is the forward path divided by 1 plus forward times feedback. That is 1 over ms squared divided by 1 plus C over ms squared. Simplify the denominator. ms squared plus C all over ms squared. The fraction becomes 1 over ms squared times ms squared over ms squared plus C. The ms squared cancels, leaving 1 over ms squared plus C. Factor out C from the denominator to get the standard form. 1 over C all over 1 plus s squared m over C. So the inner feedback loop reduces to a single block. 1 over C times 1 over 1 plus s squared m over C. Step 4. Identify G1 and G2. After all the simplifications we have, U goes through Ka, then through 1 over C, then through the summing junction where H enters directly, then through the inner closed loop block, and out comes X. Wait, we need to combine more carefully. After moving the disturbance and closing the feedback, the path from U becomes Ka divided by C. The path after the summing junction becomes 1 divided by 1 plus s squared m over C. Comparing with the target form U, G1, summing junction with H, G2, X, We identify G1 of S equals Ka divided by C, a constant gain. G2 of S equals 1 divided by 1 plus S squared m over C, a second-order lag. Notice the type. G1 is just a number, while G2 is a second-order lag with no damping term. Let us recap. We started with the active suspension block diagram from the physics modeling. It had constant gains K and A, the spring force computed from H minus X times C mass division by M, and 2 integrators. In 4 steps, we reached the simplified form. Step 1. We combined series blocks into Ka and into 1 over ms squared. Step 2. We moved the input summing junction past the gain C using Summation Move Type 2. Step 3. We closed the inner feedback loop using the feedback rule. Step 4. We identified G1 and G2 from the resulting structure. Final answer. G1 of S equals Ka over C, which is a constant gain. G2 of S equals 1 over 1 plus S squared m over C, which is a second-order lag. Same physics, cleaner block diagram, ready for analysis.